it was what was supposed to be the heart of ski season, but the resort obviously was closed. So in the photo, you can see just a sad little patch of snow in the foreground, and in the background, the mountains are brown as far as the eye can see. On the left is a figure from a paper that we wrote that was published the following year, comparing that year at I think it was 800 sites in the western U.S. That went at least back to 1977, which was the previous very low snow year. That was an extremely dry year, and that's why snowpack was low then. So all of the dots indicate where these long snow records are. And then the color of the dot indicates the ranking. So the black dots are 2015 ranked number 1, meaning it was the lowest snowpack ever. And several dozen of these sites had no snow at all for the first time ever on April 1st. It turns out that most of those dots that are not black are at higher elevation, and this is consistent with the fact that precipitation was actually close to normal in Oregon. It was drier than normal in California, but the winter was about 5 degrees Fahrenheit warmer than normal. So it just raised the snow line quite high and prevented snow from accumulating. Of course, this was followed by a warm spring and a warm, dry summer, and so we had problems with wildfires, although not as bad as 2017. There were issues with low flow and a lot of other impacts. So part of what we did in this paper is to set the context and to show that this was an unprecedented event in that we had a clear effect of warming on snowpack and stream flow. I'm going to step back and talk to you about the global science, and then we'll bring it back to Oregon primarily with Richard Whitman's talk. So 2017 was the third warmest year on record. 2016 was the warmest. 2015 was the second warmest. But we keep breaking new records for warmest ever. There was a period in the early 2000s where if you looked at this big bump in 1998, which was put there largely because it was the largest El Nino at the time, which tends to add heat globally. So if you used this as a starting point and you drew a very short straight line, you could say that the temperature had leveled off. But that was sort of silly because if you started in 1999, you could see that the warming was pretty large. So we try to be careful about not using statistics that are dependent on exactly what year you start. The overall story here is that there was a bit of warming early in the 20th century, and then a level period, and then more warming later in the 20th century. And we can sort of sort out why that happened, and I may come back to that. So this is the Joint Committee on Carbon, but I want to emphasize there are lots of different heat-trapping gases in the atmosphere. Water vapor is a naturally occurring gas, but the main thing that controls water vapor is the ocean temperature. So if we add other heat-trapping gases that warms the ocean surface, that produces additional water vapor. So that's an amplifier. Water vapor is an amplifier. But the long-lived greenhouse gases, carbon dioxide, methane, nitrous oxide, chlorofluorocarbons, sulfur hexafluoride, there's a very long list. Those are all important. This diagram focuses only on carbon dioxide, and the black arrows show where carbon dioxide was going in approximately the year 1750, so pre-industrial era. So think of this as the natural world before humans were a significant factor in the carbon balance of the atmosphere. So and this is meant to be sort of a global map, but it looks a lot like Oregon. There's a snow-covered volcano and a coastline and an estuary. So the numbers are different for Oregon, but all the same processes are active. So a couple of things to note. One, right here over land, the terrestrial biosphere has an annual breathing of carbon into the plants in the spring when they're growing leaves and stems and so on, and then respiration in the fall. And these are large numbers, but they approximately balance. Sediments carry carbon out to the ocean, and it sinks to the ocean bottom. There's also exchange between the ocean and the atmosphere. Again, pre-industrial wasn't quite in balance, but if you add up all the black arrows into and out of the atmosphere, they all balance. So the red arrows show what has happened since we started digging up fossil fuel. So this box down here shows the coal, oil, and natural gas. These are ranges because geologists are not sure how big the numbers are. But the point is here, the red number shows that we've removed 365 petagrams of carbon. Don't ask me how big a petagram is. It's a very, very large mass. And so where has that 365 grams gone? Unfortunately, the system here is blocking the top of this, but the atmospheric increase is 240 petagrams, and the annual increase now is about 4. So where have the other 125 gone? Well, most of it has gone into the ocean. So the ocean has been taking up carbon. The plants have also been taking up carbon. So growth of plants because of CO2 has been somewhat enhanced. So here's roughly 30, but the plus or minus indicates that scientists are not even quite sure of the sign of change. So I want to bring your attention back to this fossil fuel reserves. If the human race persisted in digging these up and putting them in the atmosphere, we could easily put more carbon into the atmosphere than has been present for many hundreds of millions of years. As it is, we're already at values not exceeded in at least the last 4 million years. And essentially what we've done is reverse a geologic process and put carbon into the atmosphere at a rate at least 100 times faster than it naturally would. So looking into the future, we use complicated computer programs that are sort of cousins of weather prediction models, but they're intended for a very different purpose. So they have a similar representation of the atmosphere, but they also represent the ocean, the exchanges with the land surface that you saw in the previous diagram, sea ice, and lots of other processes. The black curve, the green curve is the observed global temperature, similar to the one I showed you a couple of slides ago. And the black curve is what we get if we feed the correct information into the climate models about solar variability, volcanic eruptions, and and then to just give all the physical processes. So you can see that the climate models replicate the story of the 20th century fairly well, and generally the green curve lies within this gray shading, which indicates the range of variability. You also see dips when there were major volcanic eruptions. So here in 1961, Mount Agung, 1982, El Chichon, and 1991, Pinatubo in the Philippines. And you also see this little sort of tailing off here of those few years where temperatures look to be headed downwards. The graph ends about 10 years ago, so you don't see the big surge in temperatures since then. So going into the future, we have to make some decisions about what future greenhouse gas scenarios we want to envision. And the way climate scientists have approached this is to do 4 different families of scenarios, basically ranked from lowest to highest in how much carbon we dig up and burn. So RCP 2.6 has the climate stabilizing by 2050. So you can see the global temperatures on this blue curve level off, although there's a range of variability of how much future warming there would be. This is essentially the target of the Paris Climate Accord. So if the nations of the world work together and cut emissions dramatically, the temperatures could do this. I want to go back briefly to this. Basically, as long as the fossil fuel emissions are as high as they are now, all of these red arrows will continue. So the only way that we stop greenhouse gases from accumulating in the atmosphere is to dial back the net emissions and we can look at all of the red arrows, not just the fossil fuel combustion, but managing the land surface and possibly the ocean, combination of strategies would basically have to offset about 80% of current emissions to stabilize carbon in the atmosphere. So whether we do that at 80% below current levels or 80% at 80% of some higher levels, we could stabilize temperature either at a very low amount of further temperature change or a very high amount. So the RCP 8.5 scenario, which is the upper bound of these four, basically posits that we just continue to use fossil fuels as our main energy source globally. So there's quite a divergence in temperature between these two future scenarios using these climate models that have shown that they can replicate the temperature change of the 20th century. At the low end, if all the nations of the world meet the Paris Accord, we get a global temperature change of about 2 degrees Celsius. At the high end, by the end of the century, the temperatures have not stabilized, and they're shooting through 8 degrees Celsius, or about 15 degrees Fahrenheit, above 20th century values. So quite a divergence in possibilities based on emissions. We've done the same kind of thing here for Oregon. So this is a very similar graph. The wiggly curve is Oregon's temperatures. The black smooth curve is Oregon's temperatures as represented by the climate models. And there are roughly 20 very well-staffed climate modeling groups around the world that provide their output for us scientists to use. Instead of using the Paris RCP 2.5 as low scenario here, we're showing the RCP 4.5, which was the next one up. So this has temperatures in Oregon stabilizing toward the end of this century instead of in the middle of the century, and at values more like 5 degrees Fahrenheit above baseline for Oregon. You can also see that even here in Oregon, despite it being a small part of the land surface, of the planet's surface, that the climate models do a decent job of replicating our climate history as well. You can also see that 2015 barely edged out 1934 as the warmest year, but looking forward to the future, 2015 will remain an unusually warm year until at least the next couple of decades. If we follow the high emission scenario, it will become the norm by about 2040. If we follow the low emission scenario, it might become roughly an average year. Precipitation variability is quite large, plus and minus roughly 30% of the annual average, but it's shown no trend, and the climate models say we wouldn't expect a trend, and I can talk about why if you're curious. One of the main consequences, and this came home very vividly in Oregon last summer, is that climate warming really stokes wildfires. And so this was a paper by my colleagues John Abatsoglu and Park Williams. The figure in the paper was actually quite complicated, but I reduced it to a bar chart. Basically, since 1985, roughly 8.5 million hectares, which is more than 20 million acres, have burned in the western U.S. And John and Park estimated that if the climate had not warmed during that period, only roughly half as much of that area would have burned. Last summer, of course, was the Eagle Creek fire. There may always be idiots with firecrackers who can set fires, but with a warmer, drier summer and hotter climate, generally those fires will spread farther. And if it can burn this significantly, even in a fairly wet forest like the Columbia Gorge, this shows that the predictions that some of the climate fire scientists have been saying for years that Western Oregon could see large wildfires is coming true. And this was particularly vivid for people of Oregon because this fire, of Portland, because this fire burned right to within almost spitting distance of the Bull Run watershed that provides clean drinking water for the city of Portland and some of its suburbs. So having a major wildfire in a watershed that provides drinking water is a huge concern. Let's talk a little bit about the coast. This is a paper that came out 2 years ago. These guys looked at the behavior of the Antarctic ice sheet over roughly the last million years, and they noted that during the last glacial maximum 120,000 years ago, global sea levels were significantly higher than today, somewhere between 17 and 30 feet higher. And yet temperatures were only slightly higher than today. So given that we're clearly headed to a warmer future, they wanted to know what might happen globally. And what's shown here is the rate of flow of the ice. And so it turns out that the key for what Antarctica will contribute to sea level rise is not the net balance of how much snow falls on Antarctica and how much melts around the edges. It's about the ice flow. And around Antarctica, you have these ice shelves. So the Ross Ice Shelf is the biggest one. There's the Ron Ice Shelf and the Larsen Ice Shelf on the Antarctic Peninsula. And what they found was that there are some very surprising sudden things that can happen. And in fact, we don't have to imagine them. This already happened with the Larsen B ice shelf up here on the Antarctic Peninsula. In the summer of 2002, fissures appeared in this 600-foot thick ice shelf. And then over the course of a few weeks, the fissures turned into huge cracks, and nearly the entire ice shelf broke up and floated away. But what happened next surprised scientists. The glaciers flowing into that ice shelf accelerated by a factor of 8. They eventually slowed down and came into equilibrium with the sea, but a lot of ice was lost. And what DeCanto and Pollard found was that all of these ice shelves around Antarctica, probably during the last glacial maximum and at other periods, broke up as well. And so all of these ice streams flowing into them accelerated and delivered a huge amount of ice into the ocean. This entire West Antarctic ice sheet is sitting on rock that is well underwater. So if you melt enough around the edges, the entire ice sheet will become unstable. And that would happen over several hundred years. So my previous graph stopped at the year 2100. They have a graph out to 2500. If we follow that low emission scenario, RCP 4.5, and stabilize the climate, we still get several more meters of sea level rise by the year 2500. If we stay on the RCP 8.5 trajectory and there's these additional ice climate feedbacks, they estimate that global sea level contribution from Antarctica could be on the order of 12 meters, so 40 or even 50 feet. But you notice it doesn't even stop there. So my colleague Peter Clark at OSU was part of a team that mapped 170 feet of sea level rise. That's what they think Antarctica could contribute in 10,000 years. So the good news is that Oregon is not completely gone the way Florida is. But Salem would become a saltwater port, as would Corvallis and Albany. So, and sorry, Portland, you're underwater by then. So, clearly 10,000 years, who knows what could happen. But the point is that sea level rise is a nearly unstoppable factor, because once we reach a new temperature equilibrium, it will still take many hundreds, if not thousands of years for the ice to come into equilibrium with that new higher temperature. Richard is going to talk about Oregon and emissions, so I won't say much about that, but I just wanted to wrap up by saying I've just given you a very brief overview of the current state of global climate science. We know that here in Oregon, a lot of these climate-related risks are already here. The 2015 snow drought and attendant low stream flow, high water temperature, coastal erosion and inundation that's already happening even with just very small amounts of sea level rise, roughly a foot in the last 100 years. And then there are intersections between the challenge of reducing emissions and the challenge of living on this changing planet and reducing the risk of future wildfires, water shortages, ecosystem shifts, species surprises, coastal erosion, and so on. So I'll leave it there, and happy to take questions.